So this is our first video about stoichiometry and how we use that to solve different chemical problems. So the first couple of slides kind of explain to you guys what stoichiometry actually is, and then we're going to go through a bunch of examples together. So first up, interpreting balanced chemical equations. So here is a balanced chemical equation. I've got nitrogen gas and hydrogen gas making ammonia gas. And when I count up my atoms on both sides of the reaction, I balance it out by putting a 1 or nothing in front of the nitrogen, a 3 in front of the hydrogen, and a 2 in front of the ammonia. So what does that mean? Basically, that means that if I have 1 molecule of nitrogen and 3 molecules of hydrogen, it will react and make 2 molecules of your ammonia. So we can actually take that and expand it out to moles, okay? So it also means that if I've got 1 mole of ammonia and 3 moles of hydrogen gas, I will make 2 moles of ammonia. So have a look at this. If we look at the number of molecules, this is sort of to explain it a little bit better. If I have 1 times, so I'm showing you how this works, okay? So if I've got 1 times 6.02 times 10 to the 23, or 3 times a mole, or 2 times Avogadro's number there, I still have the ratio 1 to 3 to 2, and I end up with actually calculating out this many molecules. So I know that if I start off with 6.02 times 10 to the 23 molecules of nitrogen, and I add in 1.81 times 10 to the 24 molecules of hydrogen, I'll make 1.20 times 10 to the 24 molecules of ammonia. I'm showing you this just to, again, show you the ratio, the 1 to 3 to 2 ratio, because when we look at big numbers like this, it's hard to make sense of them. So what we've got here, this 1 to 3 to 2 ratio, is what we call the mole ratio. And that's the ratio of the amount in moles of reactants and or products in a chemical reaction. So like I've already said, in this example, my ratio is 1 to 3 to 2. Look back up at your equation. I've got a 1 here, a 3 here, and a 2 here. So I get that 1 to 3 to 2 ratio. So that's what my mole ratio is. So let's do some examples and see if we can figure this out. Okay, we're going to use some conversion factors in here and see if you can figure this out. Consider this equation right here where my red star is. How many moles of I4F2 are produced by 5.4 moles of F2? Let's look at our chemical equation. So I'm going to basically circle the 2 elements that are sort of involved in this question. So I've got I4F2, that's over here, and I've got F2, that's here. Okay, so I'm saying, if I look at just my balanced equation, I know that if I have 6 moles of F2, I can make 1 mole of I4F2, and a bunch of other things, but I'm not worried about those other things because those are the only 2 entities that I'm asking you about in this question. So I've got a 6 to 1 molar ratio. So now my question is, I don't have 6 moles exactly, I only have 5.4 moles. So how many moles of I4F2 should I make? So even just by looking at it, you should know 5.4 is a little bit less than 6. So if my ratio is correct, then I should end up with something a little bit less than 1 mole of I4F2. So how do we write this down and how do we actually calculate it? Here's what I'm going to show you. So remember when we're doing conversion factors, you start up by writing down what are you required to find. So here I am required to find the number of moles of I4F2. Then you write an equal sign, and then you write what's given to you in the problem. So in this case, it's 5.4 moles of F2. Now I'm going to times that by a conversion factor. So I'm going to erase some of the stuff that I have up at the top, just sort of color-code it a little bit for you, so you can sort of see where my numbers are coming from. So I'm going to multiply it by a conversion factor, and my conversion factor is going to have something on the bottom that'll cancel out moles of F2, and something on the top that'll keep moles of I4F2. So again, I want to cancel this, right? This is the one I want to cancel, so I'm going to write that on the bottom. So moles of F2 goes on the bottom. Now, the thing that I want to keep on the top is the thing that I'm being required to find. That's moles of I4F2. So I'm going to put that on the top. Moles of I4F2. Now I put in my mole ratio for those two entities, okay? So in this case, I have to grab them from my balanced chemical equation. So the number in front of I4F2 is up here, it's a 1, so I'm going to put that 1 down here. The number in front of my balanced chemical equation for F2 is 6, so I'm going to put the 6 down here. So I'm basically going to take my 5.4 and divide it by 6, and when I do that, I get 0.9 on my calculator, but again, make sure you have the right sig figs, so 0.90 moles of I4F2. So again, just to reiterate, my moles of F2, I've got one on top and one on bottom, so they cancel. My moles of I4F2 are here on the top. Yay, that's the unit that I want, so that's the unit that I write down here. Okay, so let's try another example using the exact same equation, and again, I'll color code it for you. Okay, so we're going to go on to question B. How many moles of F2 here are required to produce 4.5 moles of IF5? All right, so I know from my balanced chemical equation that if I have 6 moles of F2, I will make 2 moles of IF5. Okay, so the question isn't asking you, it doesn't say anything about 2 moles of IF5, it says 4.5 moles of IF5. So if I have 4.5 here, how many moles will I have to react to make that 4.5 moles? So that's what the question's asking you. So again, if I set this up with a conversion factor, again, I'm going to have the number of moles. In this case, I'm asking you to find the number of moles of F2. Okay, that's going to equal what's given to me in the question, 4.5 moles of IF5. And I'm going to multiply that by a conversion factor. So here again, let's color code this a little bit. I want moles of IF5 to go on the bottom, because that's the unit I want to end up canceling here. I want to get rid of that unit, so it goes on the bottom. Oops. Moles of IF5, there we go. And the unit that I want to keep is over here, moles of F2, so that's going to go over on the top, moles of F2. Great. So now what numbers do I put in my conversion factor? I put the mole ratio from my balanced chemical equation. So if I look back to my chemical equation, moles of F2, there's a 6. So I put the 6 with F2. And there's a 2 in front of my IF5, so I'll put a 2 there. So I basically take 4.5 times 6 and divided by 2. And when I do that, my answer is 13.5, but I'm going to round that to 2 significant figures and have 14 moles of F2. All right, so for those of you who don't like using conversion factors, I'm going to show you a ratio way to do it, so if you prefer math class, you might like this better. So I'm going to do the exact same thing using my balanced chemical equation and my mole ratio, but I'm just going to set it up a little bit differently, just to show you guys an alternate form of doing this. So let's do option C. And again, you could still do it. Now I think you have the tools. You should be able to solve question C all by yourself using this conversion factor method by putting the unit you want to cancel on the bottom and the unit that you want to keep on the top. And if you do that, you should get the right answer. What I'm going to do is show you the ratio way of doing it. So in this question, I'm asking you how many moles of I2, so that's here, are required to react with 7.6 moles of F2. That's here. Okay, so I know from my balanced chemical equation that if I have 3 moles of this, it will react with 6 moles of the F2. Okay, so it's a 3 to 6 ratio or a 1 to 2 ratio, however you want to look at it, is fine. So the question is, okay, well, I don't have 6 moles of F2. I have a little bit more than that. I've got 7.6 moles of F2. So I should expect a little bit more than 3 moles for my answer. So how would you do this? Here's how I would do it. I know that if I have 3 moles of I2, it'll react with 6 moles of F2. So that's for my balanced chemical equation. I make that equal to another conversion factor. So I know if I have 7.6 moles of F2, I'm basically asking how many moles of I2 will I have? So I've just set this up like a cross multiplication. Okay, so if you like that from math class, call this number over here x, and then do your cross multiplication that way. Okay, so you end up x is equal to 7.6 times 3 divided by 6. And you should get that your answer is 3.8 moles. And that makes sense because I knew I was going to get something just a little bit higher than 3 because 7.6 was just a little bit higher than 6. So that makes sense. So I don't care how you do this and how you solve these questions on your own, but you do have to pick one of these methods and show all your work with all of your units. All right, so stoichiometry. I'm going to give you this handout that has this sort of flow chart that you can see with all my shapes on the side. So you'll have that in your notes, as well as on a handout for you to use for the rest of the course. So stoichiometry is the quantitative calculations based on a balanced chemical equation. And we use this flow chart, again, to just summarize the steps to solving problems. So for those of you who like to memorize steps, here they are. Step 1, you always need to have a balanced chemical equation for the reaction. Step 2, you have to determine the number of moles of whatever I'm giving to you in the question. Then, using step 3, you're going to use the balanced equation, so you're going to use your mole ratio to determine the number of moles of the substance you're looking for. And then the last step is convert that number of moles to the units requested, which is usually mass. Okay, so for the rest of this unit, we're pretty much going to be dealing with mass conversions. So if I flip this over to the next slide, you can see, oh, you can't really see that. It's pretty faint. Oh, I might have to write that in. So up here, this is the mass of A. We use the conversion factor, which is the molar mass. So I'll just write mm. And that gives us the moles of A. Then we use the mole ratio. Okay, that gives us the moles of B. And then we use the molar mass of B to convert that to the mass of B. So those are our steps. If you like using flowcharts, it's there for you. If you want to memorize steps, it's there for you. Or if you want to just use conversion factors, you can do that as well. All right, so let's look at this example. How many moles of oxygen are required to produce 242 grams of magnesium oxide? What mass of O2 is required? So I'm looking to find the moles of oxygen and the mass of oxygen. So step 1, oh, shoot, sorry, I thought I had the steps written down there. So step 1, I need to find a balanced chemical equation. So I'm producing magnesium oxide. It said that right here in the question. So I know that my products are going to be MgO. So from that, I know I need to have Mg plus O2. Okay, so it's a synthesis reaction. And then to balance everything out, I'm going to have a 2 in front here and a 2 in front of my Mg. So there's my balanced chemical reaction. And that's step 1. Step 2, I'll do it in a different color. So step 2 is going to be converting the mass of A to the moles of A. So in this case, I use the 242 grams of magnesium oxide, and I'm going to convert that to moles. Okay, so I've got 242 grams of this stuff here. Okay, I'm going to convert that to oxygen. So that's sort of the flow that I'm going in here. So how do you convert from mass to moles? I use the molar mass. So in this case, I want to find the number of moles of, oops, not Mg, MgO equals, what's the number given to you in the question? It's 242. And I'm going to times it by a conversion factor. So in this case, grams needs to go on the bottom so that they'll cancel out. And moles over here is the unit I want to keep, so that goes on top. And then what I do is I plug in my numbers. So what numbers go here? This is the molar mass. So I put 1 mole divided by 24.31. So when I punch that into my calculator, I get 9.954751131 moles, and that's moles of MgO. Oops, I did that wrong. Sorry, I was doing just magnesium, so this molar mass is wrong. So this is 1 mole, and magnesium oxide is 40.31. My apologies, guys. Okay, so when I calculate that, let's try this again. I get 6.00347 ... moles of MgO. Okay, so again, my grams cancel out. I get the unit that I want to keep, which is moles. So now step 3. This is the new step. Okay, everybody should have known how to convert from moles to mass by now and mass to moles. So step 3, I'm going to use the mole ratio and go from moles of A to moles of B. So in this case, I'm going from moles of MgO to moles of O2. That's what I want to do. So I'm going to use my mole ratio. So the number of moles of O2 is the next thing I want to find. So I'm going to use the number from the problem right before, or the step right before, and that's moles of MgO. And again, multiply it by a conversion factor. So here is where, again, you have to figure out what you want to cancel and what you want to keep. I want to cancel out moles of MgO. I don't want to have that unit. I want to get rid of it, and I want to keep moles of oxygen. So I put that on the top. And now I fill in my numbers. So what are the numbers that I'm going to fill in here? They're from my balanced equation. So I have a 1 in front of my oxygen, so there'll be a 1 there. And I have a 2 in front of my MgO, so I'll put a 2 there. So I take my answer there, times 1 divided by 2, and I get 3.001736 moles of O2. So that actually answers this first question. How many moles of oxygen are required? I need 3 moles of oxygen to react and produce 242 grams of magnesium oxide. Second part of the question is what mass of O2 is required? So that's step 4. So if I'm finding mass, I've got moles of O2. I'm going to go back and convert that to mass of O2. I'm going from moles to mass. So the number of grams of O2 equals my moles from the previous calculation times, in this case, a conversion factor that's using the molar mass. So again, I want to put moles on the bottom to cancel out and grams on top. So what do I put in? I put the molar mass of oxygen, O2. So that's 32.0 grams for every 1 mole. So I take my answer times 32, and I get 96.0555 grams of oxygen. And I have to remember to round this to my right number of significant figures. Okay, so here in the question I had 4. And in every other step I had at least 4. Here I used 32.0, so I should actually round it to 96.1 grams of O2. So if I burn 96.1 grams of O2 and react it with enough magnesium, I should make 242 grams of magnesium oxide. All right, example number 2. What I think I'm going to do here is put up the final answer and see if you guys can get it. So if you guys want to pause your video. So your answer should be 136 grams of O2 at the end with significant figures and units. So give that one a try. If you'd like, we can take that one up in class if you can't get the same answer as me, but try to follow the same steps as we did on the last slide and go from there to try to figure out. So you have the balanced equation, find the moles of potassium chlorate, convert that to moles of oxygen, then find the mass of oxygen. So that's it for this, video. Your new key terms are stoichiometry and using the mole ratio to solve problems. That's it, that's all.